So as you may have noticed in the program, I have two presentations. So today, this is more like a tutorial introduction to differential privacy, and tomorrow I'll be talking more about kind of a new research. But hopefully this will be kind of, also some new angles here. So trying to take a rather modern approach. Compulsory introduction. I guess we've all seen these examples quite a few times so far, that if you have a machine learning model, they do have a tendency to memorize their training data, and especially with generative models, it's often possible to also extract some of these. What might not be so familiar with you is that under ideal conditions, so it's also possible to show that even discriminative models, like a classification model, do memorize their training data. And this is an example, kind of really under ideal conditions, from a paper by our yesterday's speaker, Borja and colleagues. They were training classification models under the assumption that the adversary knows everything except a single example in the data set. And then they were building a model to reconstruct that single missing example. And these are the results. So basically, although it's not a practical attack, it does show that the models do memorize these individual examples. Then the question is it possible to extract them in practice? Federated learning is another technique that, especially in the health domain, is often suggested to preserve privacy because the data stays on the client device and you can't then recover it. Well, as you are sharing these updates in federated learning, obviously these will contain information about the examples, and I think we've already seen some examples of how these can be reconstructed. This is when you have a passive adversary. If you have an active adversary who kind of wants to design a model that can reconstruct these examples, then you can basically have kind of like perfect copies of individual training examples. So how these map and kind of, how to formalize this. So Andrew was already talking about this yesterday. There was this inferential, I don't remember what was the precise word they had for this, but basically these privacy attacks. There's basically 4 of them that are related to extracting information about the training data from the model. So these are membership inference, attribute inference, training data reconstruction, and property inference. From the perspective of kind of privacy and differential privacy, I focus on the first 3. I'm not talking about property inference, which it's kind of a debatable whether this is actually a privacy attack. So this is basically the idea of property inference is that you want to learn some statistical properties about the training data set. This is about what was the fraction of people of a particular ethnic origin in the training data set. And this isn't so much about individual privacy, but it's about kind of group level. And so it's kind of in a different class. But okay, what do they, very quickly going through what are the other attacks? So membership inference, this can be formalized as games. And for membership inference, a simple illustration is that there's kind of the challenger at random picks one of these two models. So they kind of either train a model with this cat image or without, and then the adversary, given the trained model, needs to identify which one of these two cases it was. And so membership inference, they want to infer whether this cat was part of the training data or not. Attribute inference, this is now, for membership inference, it's kind of, you can ask the question, and especially kind of if you come from a more information security background, okay, why is this an important attack? Because, the adversary has to know the target data point. So it's kind of not something that, probably makes big headlines. The others are easier. So for attribute inference, the idea is that you have a trained model, including this target example, and then given a part of that target example, you want to infer the rest. And training data reconstruction, obviously, now you just have the trained model, and you want to infer the target example from that. What's interesting, I mean, there's some work I don't have the time to go into, but I'm happy to chat offline, is that, I mean, there's some work that shows that up to constants, these first three are actually equally difficult to defend against. So if you can defend against one, then that's also defense against others. And maybe this is why kind of, I mean, actually membership inference might not be such a bad idea to study. And when we talk about differential privacy today is because with differential privacy, we can provably protect against all of these first three attacks. Okay, so that's for motivation. Then to get started what we are. So basically today I'm going to give a somewhat unorthodox introduction to differential privacy. We develop this more from a statistical perspective of thinking about, okay, how does, I mean, we have an adversary who wants to distinguish whether a particular example is a member or not. How do we bound this distinguishability? And from this, how can we derive a privacy definition, which we'll talk about things like trade-off curves and ending in the definition of so-called F differential privacy. And then we get to the usual kind of different variants of differential privacy that you will see, but then these sort of fall out as special cases of the FDP. And this will provide kind of, in my opinion, a better insight into what do these actually mean, these different forms. We will quickly go through the basic properties of differential privacy as well as think about the basic DP mechanisms. But this is sort of as far as we'll get today. And then tomorrow is more about kind of actual applications into deep learning. Okay, and yeah, by the way, I mean, if you have any questions, feel free to raise your hand and interrupt. It's kind of, in a 1.5 hour talk, it's easier to do those questions right away rather than at the end. Okay? Okay, so let's get started in working towards differential privacy. This is a picture I've been using to introduce differential privacy for a long time, but now for the purpose, usually there's kind of the equation at the bottom to define what is DP. So how do we bound these things? But now let's start without that. So basically, differential privacy is a property of an algorithm, and it's based on a kind of thought experiment that we have two data sets that differ by a contribution of a single individual. And then we look at what happens if we apply the algorithm to this pair of data sets. And basically, we want something like from any output of the algorithm, an adversary shouldn't be able to tell too accurately whether the input was D or D prime. I'm being very fuzzy here about what does it mean that the adversary shouldn't know, and this is kind of where the plethora of different definitions of differential privacy come into play. But things to note is that, I mean, it's a property of the algorithm. It's something you prove mathematically, and it's kind of a worst case. So the whatever property we have has to apply for all possible pairs of data sets that differ by this single individual's contribution. Okay, so how do we go about in kind of thinking about this distinguishability? So let's start with a very simple setup. Now we have a sensitive data set, and there's two possible options for that data set. So we have 1 bit, that's either 0 or 1. This is our sensitive data set, and then kind of our neighbor is that, I mean, which kind of we get this neighbor by flipping that bit. And now we want to protect whether, now we want the adversary not to be able to infer whether our data set was 0 or 1. And as the algorithm that we use to protect this, now we work in a continuous domain, which might not be that relevant for this protecting bits, but this is kind of course, I mean, for many applications we will be working with real numbers, so this will kind of make things easier in the future. So our mechanism or algorithm, I'm using MD to denote the algorithm. It's commonly called mechanism in differential privacy. So we take our bit, and then we add Gaussian noise to that with some variance sigma squared. Okay, how does this look like? Here is our, so we can get, basically, in the case our bit is 0, which was denoted by blue, we get this blue curve, which is the output distribution of the mechanism. In case it's 1, we get this red curve. And this is assuming we add noise with a unit standard deviation. Okay, so far so good. And so what we can see here is that this probably would give us some privacy protection. There is this overlap that if the outcome would happen to come from this overlap, then we are pretty sure that, okay, it's going to be, so we can't really say which one it is. But if we happen to kind of draw an example that's somewhere at the tails, this is not going to be super private. So there's kind of a risk that we might end up revealing quite a lot. How to make it more private? Well, just increase the noise. That will then make it more private. Of course, then you don't really learn much about whether it was really a 1 or 0 if you have this much noise. So you might also want to add less noise, but of course then there will be very little privacy. There's very little overlap with these. Okay, I mean that's kind of very intuitive, but I mean how do we formalize this? So basically if we look at this from an adversary who kind of after observing the noisy outcome wants to infer whether it was 0 or 1, this will be a binary classification problem for the adversary. And so I mean, just to get into standard terminology, we can fix that, let's call 1 the positive and 0 negative. So we have this table of possible outcomes. If it's really 0, the adversary predicts 0, it's a true negative. If it's really 0, adversary predicts 1, it's false positive. If it's really 1, we predict 0, it's false negative. If it's 1, 1, 1, true positive. So this, I guess, should be familiar to most if you've been looking at classifiers and how to understand classifiers. But yeah, so now kind of, I mean, just looking at these single examples, it doesn't tell much. So really kind of what we want to understand this is statistically what happens when we repeat this. So we will look at rates of different outcomes. And we get these things that you probably have seen if you've been looking into classification. So we have a kind of the ratio of true negatives over all negatives is called the true negative rate. Ratio of false positives over negatives is the false positive rate. False negatives over positives is the false negative rate, and true positives over positives is true positive rate. I hope this is familiar and you've at least seen some of this before. Okay, so so with these we can then, if we know these different rates for the classifier, we can then characterize its performance. And basically, if you want to have these different, basically any metric that I mean you would use for to describe a classifier, you could typically derive from these. So what's the accuracy and these F1 scores, sensitivity, specificity, whatnot. Okay. So in our case, so then next step, how do we define this classifier that we are looking at? In this simple case where we have kind of like 2 values, and kind of adding noise from a well-behaved monotonic distribution, it's probably a pretty good strategy to just pick some cutoff that I've denoted by gamma here, and then predicting that when the value is, the observed value is less than gamma, we call it a negative, so we predict 1. And if the value is greater than gamma, then we predict 1, so we call it a positive. Okay, pretty simple. Obviously, I guess, the obvious thing kind of now, you might be thinking, okay, why on earth did I pick this gamma to be here? If you want to maximize the usual accuracy, you would pick it somewhere in the middle. This is kind of where we come into this kind of question of how do we weight these different kind of errors. And this is kind of a big part of the story here. So here, by pushing the gamma more to the right, I am kind of making fewer positive predictions. I'm making way more negative predictions, which also means that I'm making way fewer false positives at the expense of having more false negatives. So there is this trade-off that we can make, and this trade-off is really the thing that we are going to get into. Okay, all clear so far? Okay, so how do we characterize these different errors that we had in the table? It's actually, you can graphically plot it. It's kind of, if you think about it a bit, it's pretty straightforward. So true negatives, you look at the distribution of the negatives, so that's the blue curve, and then you look at the ones that were below gamma. So those are the true negatives. False positives, we look at the blue curve. Those are the other half of it. So those were the blue curve was the negatives, so the ones that are predicted positive would be the false positives. And similarly for false negatives, false positives. So this is all just looking at these distributions and then looking at the mass that follows on either side of this gamma. And if we look at kind of now focus, so for the rest of it, we kind of ignore the ones that we predict correctly, and we really want to focus on the false positives and false negatives. And so for that, we can now have a look what happens when you change the gamma. Again, it should be fairly obvious. If we start with a small gamma, we will have very few false negatives, but a lot of false positives. And as we increase gamma, we can kind of make different trade-offs between these. So this would be kind of like the balanced classification case at the midpoint. And then if we care more about we want to avoid false positives, then we might push the cutoff further to the tail. In the extreme here, there's a lot of false negatives, but we are making even fewer false positives. Okay? Okay, let's turn into a bit of math. Kind of fresh wake up from morning. So let's work out what would this be mathematically. These different rates that we have here. So starting with the true negative rate, and assuming we have the cutoff gamma, what is, so true negative rate was the kind of rate of true negatives over all negatives. So basically we are looking at what's the probability mass of this magenta part here. Any ideas? Anyone awake enough this early in the morning to think about? I mean, how to derive this? How could we derive this? Integration of the curve up to this point. Okay, we have what we have here, kind of with sigma equals 1. This is a standard normal. So how would you integrate the standard normal? Sorry. CDF. Yeah, so we have the CDF of the standard normal. That's a very good bet, guess, or no. So how would we precisely get? Where do we evaluate the CDF?
About 60-something%.
Well, I mean, we have basically, so I mean, we have we have the distribution centered at 0, and we want to know what is the mass of that distribution up to cutoff gamma. Yes. So this is, yeah, it is the CDF. It's the definition of the CDF at gamma. And if we generalize that a bit, if we change sigma, we would have, in general, the CDF at gamma divided by sigma. Okay? Okay, so now that we know that, the other ones should be easier. What's the false positive rate? 1 minus. Yeah, so it's the density integrates to 1. We know what's the mass of the left-hand side, so the right-hand side is simply 1 minus that. Okay. False negative rate. It's the same kind of thing. We are looking at the CDF. Now the only catch is that the distribution is shifted a bit. Namely that the center will be at 1.
Gamma minus 1?
Yes, so we simply replace the gamma here with gamma minus 1. Yeah, and otherwise it's the same. Good. And true positive rate.
Complementary?
Yeah, so this is again using the same rule, 1 minus the rest. Okay, very good. Good news. This was the most difficult part of the math to kind of deriving FDP for the Gaussian mechanism and a lot of other things. So this is, we are kind of done. Now we've done the hard part. Okay. So this is basically what we need. And namely, we will need these two quantities here. So like I was saying, we focus on the false positives and false negatives. So what we need are the false positive rate and the false negative rate. And so this is a way kind of, I mean, how this is, these distinguishers are commonly summarized using so-called trade-off curve, which basically is that we plot the false negative rate, which is denoted by beta, as a function of the false positive rate denoted by alpha. If you're familiar with the ROC curve, this is essentially the same thing except you flip the y-axis. So ROC curve would plot the true positive rate as a function of false positive rate. So you have kind of like the 1 minus there. Don't ask me why they kind of don't do it with ROC, but rather the trade-off. But this is how it works. Okay, so here we have a formula that given gamma, we can find these points on the on this trade-off space. So we can plot these. So, and now we can take the different values of gamma we had in the previous plots, and we can find what is the corresponding false positive rate, what's the corresponding false negative rate. And we can see, as we kind of suspected there, that if you take the, I think I had even further. So if you take kind of the very large gamma, you will have a pretty high false negative rate, but you will also have a very, very low false positive rate. Okay, this is for individual gammas. Of course, we can also kind of, just connect these with a curve to get the entire profile. And really, when we're analyzing algorithms, we don't really care about gammas, so what we really want is the curve. Okay, so how do we get the curve? So we can actually solve this pretty easily. So we have the expressions for the alpha, the false positive rate, and beta, the false negative rate. Now I'm kind of simplifying this a bit because we had this gamma minus gamma over sigma, so we can kind of just expand this to get the gamma over sigma there as well. And so from the first equation here, we can solve gamma over sigma. It's just kind of moving this to the other side. So we have this CDF expression being equal to 1 minus alpha, and then you take the inverse of the CDF, so we get this gamma over sigma being inverse of the CDF at 1 minus alpha. Okay. And now if we plug this into this expression, here we get, so this is basically, it's just this expression where we have substituted this for the gamma over sigma so that we can eliminate the gamma. Okay, so now we have a general expression for the trade-off curves that just depends on the, so trade-off curve is beta as a function of alpha, so it depends on the alpha, and otherwise it just depends on the CDF and the sigma parameter. So we can easily plot this for arbitrary sigma. If we do this, this is for the Gaussian. So we get these plots that see, you can see that when you increase the sigma, so adding more noise, these curves will approach this dashed line here that is like kind of in the ROC curve you have this random guessing level. So this is the same here. That it's the dashed diagonal is a point of no distinction. That would be fully private. Then the adversary couldn't learn anything. And then as we decrease the noise, the curves go closer and closer to the bottom left. If you are very careful, the red curve here, there is actually a red curve here. It's just super close to the origin. So this is something that doesn't really. You can see that it's kind of at a pretty low false positive rate. You can get a very low false negative rate, and this is the kind of, if we think about privacy, this is something that doesn't really provide you with much privacy. So here, intuitively, kind of the diagonal would be perfect privacy. The closer you get to the bottom right, the less private it is, because then the adversary could really would be able to classify these with making very few false negatives and false positives. Okay. So what else? The interesting point here is that the expression we derived it for the Gaussian, but it's actually kind of very general. So we just need something. We need the CDF. So we kind of get these models for other kind of these trade-off curves for other noise distributions for free. So just for the fun of it, here is the corresponding curves for the Laplace noise. That's often used in DP, and so we can see that it's not clear that one of them would be more private than the other. They are just different. So this is Laplace, this is Gaussian. There's a different shape. Something you can see that in the Laplace there's kind of like this long kind of it looks very linear for a long time before there's this slight bend, and this is something we will come to in a minute. Okay. Any questions so far?
So may I just ask, maybe it's not intuitive. So wouldn't we? So those are false negative and false positive. But if we don't infuse any privacy, we may assume that we have a perfect guess each time. Why would we have false guessing? Why they alpha and beta sum in 1 and not in 0 when the privacy, there is no privacy?
So when there's no privacy, we would be kind of like at 0, 0. No false positives, no false negatives. So the diagonal line is perfect privacy. Sorry if I said it the other way around.
Okay.
Okay. Yeah. So diagonal line is perfect privacy. So it's basically that we can. It's the same as kind of the random guessing level in an ROC plot. So if you really don't know by simply guessing a certain fraction of positives, certain fraction of negatives, we can realize any point in the on the diagonal, but it's just random guessing. So we don't learn anything.
So the dotted line has variance approaches infinity, right?
Yeah, you would get to that as variance approaches infinity, or you could also get to it with a mechanism that kind of, just doesn't use input data at all. So something that's kind of perfectly private. So if we did a mechanism that's kind of independent of the input data set, then obviously the attacker wouldn't get any information from that, and the best they could do would be just to guess randomly. Sorry, so at 0 false positive, false negative, your model has?
Yes, because here when you said that, okay, when the sigma is 0, so you don't apply any privacy. So you assume that when your curve completely is like this, so you assume that your model is, the prediction is very perfect.
Yes, so basically, if you don't add any noise, you would be basically at this corner, which is that then the adversary kind of, just looking at the input, they could perfectly predict which one it is. So yes, that would be the fully non-private solution. Okay, so clearly these kind of curves tell something about the privacy of the mechanism. And so this is something that has been formalized as this so-called F differential privacy. To get formally into this, we want to define this trade-off curve that is essentially what we were looking at, but now we are taking kind of, just the minimum over all possible distinguishers, just to make sure that, this is really, we have the adversary is using the best technique that they can. And so with this, taking the minimum over all possible distinguishers, we can define that if an algorithm for all possible pairs of adjacent data sets, so this was these data sets differing by contribution of a single individual, you can't distinguish from the output those data sets better than some curve f, then that mechanism is said to be F differentially private. So what does that mean? Basically, we could take, say, one of these Gaussian curves as our baseline, and then saying a mechanism would be f differentially private with this Gaussian trade-off curve if the actual trade-off curve for that mechanism is always above that particular line. So it's less distinguishable than what the f curve that we are comparing against would be. Okay, so that's it's kind of we have a very general formal definition of differential privacy. Let's then look a bit next how this links to forms you might have probably seen more out there. So the question is, okay, this is, yeah, the f is nice, but it's kind of difficult because, I mean, then you're kind of, typically kind of when we talk about dp, you've seen that, I mean, you have this epsilon, and epsilon is a real number, so you can say epsilon 1, epsilon 5, epsilon whatever. With fdp, your privacy parameter is a curve. It could be kind of like well, not arbitrary, but I mean, pretty complex function from in the reals, so it's kind of hard to distinguish. So it's good to have some simpler forms to bound this trade-off function so that we get simpler kind of things that are easier to communicate. And with this, we actually get to the classical definitions. So the first very simple way we can think of for bounding these trade-off curves is that we take a piecewise linear function that's just consists of two pieces. So we have kind of like so these trade-off curves, by the way, I mean, they have to be symmetric around this kind of y equals x line. So basically there's not that much freedom. So for this simple curve, we simply have kind of like this some negative slope here up to a point on the y equals x curve, and then it's mirror here. And if we choose to parameterize the slopes conveniently, so for the first part, the slope will be minus e to the epsilon, and for the second part, it would be minus e to the minus epsilon. It turns out that this is actually equivalent to the standard epsilon differential privacy. So here, kind of, we can see visually how epsilon differential privacy looks like. And again, I mean, if we have kind of like epsilon gets smaller, then the slope here gets closer to -1, so you get closer to the perfect privacy. And as epsilon gets larger, then this slope here gets bigger until eventually you get kind of very close to the origin. So it kind of works as we would expect. Okay, so epsilon dp, we can also define in a more classical way. So this is, we can look at the probabilities of outputs of the mechanism, and when these are bounded by e to the epsilon, then this is epsilon differentially private. In case of pure epsilon dp, we can either look at the point probabilities or probabilities of outcomes in a certain set. Okay, so basically, I mean, if we kind of now turning from the FDP to the classical epsilon dp definition, basically what this says is that for all adjacent data sets, the ratio of probabilities should be bounded. So there would be kind of basically for all pairs of adjacent data sets under pure epsilon dp, it should be possible to get any outcome from either of those. So with this kind of thinking, let's kind of think a little bit, look at, what, for certain mechanisms, let's think for a bit whether these are differentially private or not. So just to formalize it, we assume that our data set, we have a set of n real numbers, and now we have a mechanism that computes the median of those numbers. Is this differentially private? No, there were some shakes. Why? Yeah.
Can we say it's actually epsilon dp but infinite?
I guess usually you assume that it would have to be kind of finite, the epsilon, for it to make sense. If anything is kind of if you allow epsilon to be infinite, then anything would satisfy. The definition would be meaningless if you allow epsilon to be infinite. So that's we only consider the case where epsilon is finite. Why is it not dp? Yeah.
And we can imagine so the distribution, the data set where we have all zeros, one half in the middle, and all ones. And so the median would be one half. But if I change this one half to something else, then the output of the mechanism would change dramatically, and it can't be really controlled nicely.
Yeah. So basically, we can make it extreme, or we can, I guess, in this case, it's basically, any, if you kind of, let's say that, all the values are unequal. If you change one of the values, the median would change. So clearly it will not return the exact same value. Yes?
It's not clear to me how the median would change if you change a value, say a value that's...
Okay, yeah, sorry, yeah. So you need to change a value that's kind of like the middle value, or, so it doesn't have to always change, but there are examples where it changes. Sorry, yeah,
So
thanks.
Is it dp, epsilon dp conditional on certain change, or how do you define this?
So for it to be epsilon dp, this would need to happen for all pairs of data sets. You need to have this condition. So if you can find even one data set where it doesn't satisfy it, then it's not going to be epsilon dp. So epsilon dp is a worst case property over all data sets or pairs of data sets. Very good question, thanks. Okay, what about next one? Is this dp? Maybe we do a quick vote. So who thinks this is dp? Who thinks this is not dp? Majority for yes. There's a probability 1 that it will return 5 regardless of what the input is. So clearly this is epsilon dp with epsilon 1, sorry, epsilon 0. Okay, then a different one. So let's take a mechanism that picks one of these input points uniformly at random and then publishes that value. Is this dp?
Yeah, sorry, I'm just answering
Okay.
yes.
maybe we do a vote again. So is this dp? Yes. A few. Is this dp? No. Kind of lots of uncertain. So which way do we want to? Maybe we start with a yes. So why would this be dp? Because it's random, okay. Why would this not be dp?
Let's take one set of all zeros and one set of all ones, then we can perfectly distinguish them.
Okay. So the suggestion was to take one set of all zeros, one set of all ones. yes, we could perfectly distinguish them. The problem is that those probably are not kind of adjacent data sets differing by one sample. So the idea is that, I mean, you have to, you only change one individual. But, I mean, we can build on that. So we can do a data set of all zeros, and then we can kind of do an adjacent data set that adds a single one. And now there is one of these mechanisms will always return 0. One of them will occasionally return 1. And this is enough to break the condition that we had. So this is not DP, which of course is good because, to be honest, this wouldn't be very private. If you could kind of take a big database and then randomly publish a single individual's data, that wouldn't be kind of like what I like to think about private. Okay, last one. So we take the sum of our input points, and then we add uniformly distributed noise with kind of from between -1 and 1. Let's think for a bit, and then we can vote again. Okay, so is this epsilon differential private? Yes. Is this epsilon differential private? No. Kind of like pretty even. Okay, let's have some justifications. So someone who voted for yes, why is this differential private? Anyone? Yep.
So when you aggregate, you sort of lose out all of the individual properties, and then you're just having some sort of random noise.
Okay, so this is kind of idea. Yeah, we aggregate, we take the sum, we add random noise. This is something, ingredients to make it private. Okay, good. Then from the nose side, anyone? Yeah?
I think it's not DP because if you replace an element, it's very different from the original dataset. So you can perfectly distinguish them.
Okay, yeah. So that's a very good answer. So we can kind of think about the same example we had before, because we only need to find one pair of data sets for which it doesn't work. So let's take a pair of data sets where in one of them it's all zeros. In the other one, it's all zeros except one of them is equal to 10. And now if you think about kind of what are the distributions of outcomes, in one we have a uniform distribution and kind of a narrow uniform distribution centered around 0. In another one we have a uniform distribution centered around 10. They're completely disjoint. So from observing the outcome, you can perfectly tell which data set it was. So no, it's not private either. Is it kind of clear, somewhat clear at least, kind of why this is? So kind of starting to develop some kind of idea of what makes things differentially private and what is not. Okay. Yes.
Would this change if the uniform noise space would be bigger if our numbers get bigger?
So with uniform noise, I mean, unless kind of you have somehow kind of bounded space, and that uniform noise would cover the entire space. With uniform noise, you can't typically make things pure epsilon dp. You would need something that kind of extends to infinity. So the Laplace noise we had earlier, which is like double exponential, that would be an example of a mechanism, that kind of noise distribution that gives you epsilon dp. But it's really kind of, you have to have kind of like that. The possible set of values is the same in both of them, but even that's not sufficient. That if we added Gaussian noise, there's kind of the tails would decay too quickly for it to satisfy the definition of epsilon dp. We'll get to that kind of in a more kind of from the FDP perspective in a bit. Okay. So really, kind of something that we have somewhat glossed over here is this definition of neighboring data sets. So I'm kind of just thinking, okay, changing a single individual. The figure I had at the beginning was actually based on this interpretation number 2, which is called bounded DP or substitute neighborhood, where kind of these neighbors are obtained from one by replacing one entry. Another very commonly used one is what's called unbounded DP or add remove, where you add or remove one entry. And this is, as you can guess from the names in the first case, it's kind of interesting because the neighboring data sets are of different size. So it's, in this case, if you can observe the size of the data set, you can tell which one it is. In this second case, they are always of the same size. And you need to be careful with which one of these it is, because these are not directly compatible, and there's a lot of theory that only applies for one of these and not the other. So I think, we are kind of, as a field, not being very careful, but it would be really kind of, if I got to choose, I really would like kind of people to be more explicit about this, and kind of when writing talking about DP, then including what is the adjacency. There's also another dimension of the adjacency that we'll get back to later, which is the question that, okay, do we, for privacy, it's kind of usually think about it as kind of a user level. You replace data for one user. In some applications, if you talk to the DeepMind folks, for instance, they kind of see that, okay, it's very hard for Google to find out what is all the data about a single user. So they kind of prefer to define this on a level of, on some kind of more fine-grained level of some contributions, like images or kind of a piece of text or something like that. Yes?
Yeah, I have two questions. One regarding the last slide. So we have a mechanism which is a deep DP and a bit more interesting than constant.
Yeah, we will get to the more interesting mechanisms in a bit.
You presented two definitions. Which of the definitions has, in a sense, more theory or more results proven for it?
So from these,
Yes.
so I would say that especially kind of when we get to the deep learning, a lot of that is built on the add remove. Some, especially kind of when we are talking about differential private stochastic gradient descent, you will be kind of doing subsampling and then adding noise. And this, for many things, this is easier to analyze in the add remove case. Just kind of, thinking about what privacy means, I kind of personally have some fondness towards the substitute, which is kind of, yeah, you can't learn about my data because, the result would be the same even if you replaced all of my data set, which is kind of, different idea from, okay, what if you removed my data set and my data? It's, the distinction is subtle, but it is there. And yeah, there's some things that, there's also kind of, under the add remove, it's kind of like, there's this question, should we keep the size of the data set secret? Because, technically, if you know that, then you can distinguish immediately what it is. Okay, yes?
The first one doesn't imply the second one?
So you can, by combining kind of one addition and a removal, you can get the second. So it's kind of like that you need kind of another property of DP, which is kind of like you can do multiple of these operations. So yes, it's yeah, that is true. So yeah, you can kind of like add one, remove one, and then that would be a substitution. So yeah, there is that. Good. Yes.
You kind of glossed over this, but when we're working with DP, how do we recognize which interpretation is more appropriate for our work, or easier to work with?
So the question was, when we're working with DP, which one is easier to work, or which is more appropriate? That's a very good question. I guess, I mean, for some cases, I mean, the application might define that, I mean, one of them is more natural than the other. I think, I mean, a more pragmatic approach is that, I mean, you just look at kind of the methods you want to apply, which one are they using, and then you use that definition and hope that it works for your use case. Okay, moving on. So that's pure epsilon dp. I guess, I mean, if you are familiar with dp, you might have also seen this more commonly used one called approximate dp or epsilon delta dp, which was originally defined because kind of the pure epsilon dp is very restrictive, and I mean it's you can't, for instance, I mean adding Gaussian noise wouldn't satisfy the pure epsilon dp. So with epsilon delta, we now take another piecewise linear approximation of the trade-off curve. So, but now that's kind of, we first add this slack term delta. So kind of before you start going diagonally, you first go down delta, then you have this slope minus e to the epsilon, and then symmetrically. So we have this bit of slack. So we are kind of, I mean, you can have, so under epsilon delta dp, you can have a kind of a at zero false positive rate. You can have kind of false negative rate that's not exactly 1, but close to 1. So there is certain probability of complete failure. And so this is corresponds to the approximate epsilon delta dp. And so traditionally, the definition is also written similarly in terms of these probabilities of outcomes. But now we need to add this slack term delta here. That's ideally meant to be for low probability events if we kind of think about this from the epsilon delta definition perspective. Now when we look at this, I mean, we kind of have to do this, that, I mean, it's probability in a set, not a point probability, because, I mean, the delta wouldn't make sense in the point probability setting. There's also a very common misconception that this epsilon delta dp would correspond to epsilon dp with probability 1 minus delta. Unfortunately, as nice as it would be, this is not true. So there's kind of like not, at least I'm not aware of kind of an easy interpretation of what this means, except it's you have this bound, then with the slack delta. I guess, I mean, this is really kind of, doing this plot is really kind of the most intuitive explanation of what the definition means.
So, but having epsilon dp with probability 1 minus delta would satisfy epsilon delta?
Yeah, it implies it, but not the other way around. Yeah, so there's they are two different concepts, and basically meaning that, I mean, if you have epsilon delta dp, it does not imply that you would have epsilon dp with probability 1 minus delta. Yeah, okay. And so, I mean, in the usual theory, there's kind of like, because, I mean, the delta is this failure probability, so it should be set to a very small value. We had this mechanism that kind of randomly picks one of the random participants' data and then publishes that. That would actually satisfy epsilon delta dp with epsilon 0 delta 1 over n. So, and that's not very private. So we would kind of, under this formalism, we would want the delta to be small. Okay. So our prototypical example of epsilon delta is the Gaussian mechanism. So here we have an illustration of the Gaussian mechanism with variance 1 and some possible epsilon delta curves that could be used to bound it. So this is also an illustration that I mean typically kind of when you have an epsilon delta dp mechanism, usually the same mechanism would satisfy epsilon delta dp with different parameters. So basically, because it's just we have this Gaussian nice smooth continuous Gaussian curve, we can approximate that or bound that with these piecewise linear curves. What's interesting here is that I mean typically the definition. So we kind of want to do this kind of in a case where delta is small. So if we do this in a case where delta is small, typically your small would be equal to 10 to minus 5. This is actually kind of what epsilon delta dp for this Gaussian mechanism with delta 10 to minus 5 looks like. So if we think about this as a representation of the trade-off curve, it's terrible. So this is kind of like, I mean, for those working on DP, kind of one picture to remember from this this talk is that I mean it's kind of your usual Gaussian DP, your usual epsilon delta DP with small delta tends to lead to this kind of approximations of the trade-off curve. So this is basically your bound on the success rate of the attack implied by this epsilon delta is very far from what the mechanism would actually deliver. Which is kind of interesting. So I mean, of course, I mean under epsilon delta we can have better bounds. So for instance, here we could, if we are willing to entertain kind of a pretty large delta, we can get something that's kind of like much closer to the Gaussian curve. But then that would mean that we need to have a big delta. And of course, I mean big delta in itself is bad. So this is, yeah, epsilon delta is not a very nice formalism to work with. Okay. Final way to bound this, already alluded to this, that I mean we could use these Gaussian curves as to bound things. This is called Gaussian differential privacy. That's it's defined in a slightly different way than what I did. So I was doing it kind of with mean would be either 0 or 1, and then it would have sigma. In Gaussian DP, they fix the variance to be 1. And then change the mean. So these are the same, but I mean you just kind of like would set mu equal to 1 over sigma. And so basically the expression we derived in the, for this trade-off curve is valid for Gaussian DP, but I mean you just need to set sigma to 1 over mu. Okay. So we have. That was much of the definitions. There will be a few more, but this is kind of the basic ones. Then a bit about basic properties. I'm not going to go into details, but I mean just kind of a quick overview of why DP is so useful. One of the nice features is that differential privacy, I mean, this might seem obvious, but it actually isn't. And I mean, there's kind of like many different privacy definitions. I think, I mean, the probabilistic privacy, so this epsilon dp with probability 1 minus delta would be one example of a privacy definition that does not satisfy this post-processing immunity. So basically, yeah, the definition says that, yeah, you can take the result of a DP mechanism, and then you can run arbitrary computations on top of that. As long as you don't peek at the original data, your privacy guarantees will never get any worse. And this is very useful building block for defining algorithms. There's a lot of things like, let's say many algorithms working on differential private synthetic data generation make use of this, so that, I mean, they prove that they have a generator that is differentially private, and then generating the actual synthetic data is post-processing. And what it means is that, I mean, if you have a kind of a private generator, then you can generate arbitrary amount of synthetic data from that, and it will never reduce the privacy guarantees. Another very interesting or important property is what's called composition. This is something where some earlier privacy definitions, K anonymity, L diversity, T closeness would fail. So basically meaning that, I mean, if we release the results of multiple DP mechanisms, this will be DP, but just with weaker parameters. And the details of how this works differ for the different mechanisms. I've now included here kind of, I mean, just the simplest ones. So for pure epsilon delta, you add up the epsilons. For GDP, Gaussian DP, you actually get a stronger form. So you add up the squares and they take a square root of that, which means that if we have a composition of K similar mechanisms, then under epsilon dp, you get K epsilon. Under Gaussian dp, you get square root K mu. So this is, now if you're doing kind of think about doing 100 compositions, then kind of there's a big difference on whether you have a multiplier of 10 or 100. This is also kind of, I mean, a nice takeaway that, I mean, if you are developing something that's adding Gaussian noise and then doing compositions, if you're doing the analysis under GDP, you get kind of a tight analysis essentially for free. There's also, I mean, there are these composition theorems for epsilon delta and FDP, but I mean, they don't kind of, if you want to get tight results, you can get, for epsilon delta, you can either get kind of a very loose result that's easy to write, or a tight result that's impossible to express compactly. And that's one of the topics we'll talk about tomorrow when we talk about deep learning, because we will be needing these compositions over the iterations in DP deep learning. Group privacy. So this is another one. What if we, instead of a single individual, we change multiple individuals? Typically, you just get kind of this factor of K in the added. Interestingly, in this case, it's K both for epsilon dp and GDP. For this time for FDP, it's kind of like you can write it down, but that's not super easy to follow.
So may I ask, is group privacy the same as user level privacy? But we call it not group and not user contribution.
So group privacy, I think, I mean, you could see it kind of as a, so if you have like item level privacy, and let's assume every user contributes at most 10 items, then group privacy at kind of change of 10 would correspond to user level privacy in this sense. So this is kind of like, the typical setting would be that, I mean, let's say that, I mean, you have a user level data and you have a family who are closely related, and I mean, you would sort of want to think, okay, how easily can we distinguish kind of whether this family was part of it or not? And so obviously kind of as you have more individuals, it weakens. But I mean, again, it's nice that, I mean, you can see that, I mean, it doesn't break completely. So I mean, even if you have perfectly correlated data, it could get worse. Your guarantees could get worse by at most a factor of K for K groups of K. Yep.
Could it be possible that after removing a certain number of data points, the model itself becomes less or higher epsilon d, less epsilon d? No. So then, I mean, the extreme case would be removing all the data points.
Okay. Yeah. I mean, this is an upper bound. Of course, I mean, it might be that, I mean, it's not going to be that bad. So it's always possible that, I mean, this is guaranteed that, I mean, it won't be worse than this, but I mean, of course, it could be better. So I mean, it's not. It might be that, I mean, if you're kind of, I mean, your group of K are kind of like unrelated, I mean somehow completely independent. I mean it might be that, I mean it's not easier to detect whether one of them was removed or all of them were removed. So
no, but if the model after removing one data point does not have the same epsilon dp guarantee. So it becomes more sensitive to data point changes.
dp is a property of an algorithm, not of a model. So it's maybe we should kind of think about this more offline and how that would go. But yeah, so basically dp is a property of an algorithm, and I mean it's so it's not a property of the output of the algorithm. So it's, yeah, it guarantees that some things about the distribution of the output of the algorithm. Of course, I mean it's a random algorithm, so I mean it might be that, I mean we could generate, kind of do have a dp synthetic data generation method that kind of like takes as an input a data set and as an output creates a synthetic data set. We could have an algorithm that, I mean, outputs an exact replica of its input data set. It's just extremely unlikely that that would happen, but I mean it is a possible outcome. But the point is that, I mean, even if that happened, because I mean we couldn't tell whether it was that or something else, so we didn't really learn much if the algorithm is dp. But yeah, this is kind of interesting in the sense that, I mean, you can't tell from the output whether something came from a dp algorithm or not, and what was the privacy level. Okay, I think I need to speed up a bit to make it to the end and make it to coffee in time. So, some other generalizations of dp, more definitions. You can think about these from bounding some distance of these output distributions. Commonly used examples are Renyi dp, which bounds the Renyi divergence of the output distributions, and then there's a generalization zero concentrated dp that kind of bounds these across a range of alphas, or these orders of the divergence. Maybe I don't say more about those. Maybe this is kind of interesting plot that, I mean, there is this some commonly used dp definitions, and I mean there are these relations. So actually, so at the root we have kind of like epsilon dp, which is in a sense the most special one that implies all the others. And then at the bottom we have the approximate epsilon delta dp. That's kind of is the weakest of these all. Okay. Yeah, maybe we just move on. I wanted to talk a bit about these mechanisms, and I mean there was this question of what kind of mechanisms would satisfy epsilon dp with that, I mean, I'm just not returning a constant. One example is that, I mean, if we are in this setting where our data set is a single bit, so we can also, instead of adding Gaussian noise, we can kind of just randomly flip that bit. And so basically we have that we would have probability 1 minus p of returning the original bit, and probability p of returning its opposite. So it's easy to see that the probabilities of these different outcomes are bounded by 1 minus p over p. And if we kind of turn this into exp, so we can write this as exp of log 1 minus p over p, which then tells that, I mean, the epsilon as a function of p will be this log of 1 minus p over p. We can plot it here. This is kind of a nice reference plot that I like to go to if we think about, okay, what do different epsilons mean? If someone gives you a DP mechanism and saying, hey, now here we have this very private DP deep learning model trained with epsilon 8. I kind of like to go to this plot and see, okay, epsilon 8, what probability in this flipping a bit would that correspond to? Unfortunately, my graph doesn't extend to up to epsilon 8, but as you can see, kind of it's going to be extremely close to 0 at that point. So this is really, I mean, if we think about it, kind of epsilon dp in terms of this releasing a random bit, I guess, I mean, anything beyond epsilon 3 or maybe even epsilon 2 doesn't really give you really much formal protection. They might be more private in practice, but then I guess, I mean, we are down to these questions like, okay, the epsilon delta, the figure we had, that it's actually kind of, your mechanism is actually more private than kind of what your epsilon delta guarantee might suggest. Laplace mechanism, let's see if we have time to, how much in detail we have time to go through this. So there's a very important concept here, which is that, I mean, when we're adding the noise, we have what's called sensitivity. So this is, when we are adding the noise, we have to scale it to what's the maximum change in the function value between these adjacent data sets. If you think about it, I mean, it makes a lot of sense. And I mean, it's if you have a function that, I mean, only changes very little between these adjacent data sets, then you have to add less noise. If you have a function that could change a lot, then you have to add more noise. And this is really a central concept. Laplace, I mean, just to show that, I mean, it's turns out to be epsilon delta dp, sorry, epsilon dp. It's actually not perfectly. I mean, the randomized response is perfectly captured by epsilon dp, so its trade-off curve would be kind of like this straight lines. For Laplace, you actually have this kind of like slight deviation in the middle, but otherwise it's so it's a bit more private. Laplace mechanism is a bit more private than what epsilon dp would suggest. But okay, let's and one more brain teaser with these sensitivities to get an idea of kind of how this works. So now we assume we have a data set of n real numbers that are on a closed interval from A to B. And let's consider the add-remove adjacency. So your neighboring data sets are ones where you add 1 point or remove 1 point. Now the question is, what is the maximum L1 sensitivity? So now we are looking at the one norm, the absolute value of the difference. And so yeah, let's start with the sum. So we have a sum of our values. And what is the sensitivity of this? B. Everyone happy with it being B or other suggestions? B minus A. So now we are adding 1. B minus A would be for the substitute, but I mean for the add remove it's.
It would be the maximum between B and the absolute value of A.
Yeah, that's a good. So it's really. You have to look at, in the general case, it would be kind of the maximum of the two absolute values. What about the mean?
Same divided by n.
Yeah, same divided by n. Minimum. Well, I mean, we could have a data set that's kind of all at the top end. Then we can add 1 at the bottom. So it would be, basically, we could change it by the whole width of the interval. Sum of squares.
maximum of a square and b square?
Yep. So it's similar to the first, so we just take the maximum of
May I ask about the previous plot? So you mentioned, you showed that Laplace in a sense is more private than epsilon, that it corresponds. Does it make sense to ask what is kind of the best mechanism kind of to use to have epsilon differential price?
Yeah. I mean, sure. I think there's a lot of work in this kind of like finding kind of the optimal mechanism under certain definition. I mean, the randomized response would be one that has, but if you're doing continuous, I'm not sure. If there exists kind of a continuous additive noise mechanism, that would be, but maybe that's something to
I know that Laplace is
think about.
logically optimal but not constant.
Yeah. Maybe we can continue this offline. I think I'm running out of time. So for the substitute, I'm just showing it's typically kind of you would be jumping the entire distance, except then kind of for the sum of squares it gets a bit tricky, because it depends on whether you can change things to 0 or not. Gaussian mechanism we already went through, so there's kind of like many bounds, things you can get from the FDP. If you want tight epsilon delta parameters, there's the so-called analytic Gaussian mechanism by Bourgeois and Yuxiang Wang. The math looks a bit messy, but you can find implementations of this. And so yeah, this is basically kind of what I used to compute these bounds here. It's interesting that so for the, I guess the typical bound you've often seen textbooks, and unfortunately people still sometimes use, is this epsilon kind of this classical Gaussian mechanism bound that has this weird 2 times natural logarithm of 1.25 over delta times something. An important thing to note is that this is only valid when epsilon is less than 1. And another thing to note that it's pretty weak. So in this particular case, the only value where I could compute this kind of bound for this Gaussian mechanism with sigma equals 1, assuming sensitivity 1, was at epsilon 0.8, where we get a delta of 0.908, whereas kind of your analytical delta would be way smaller. Okay, I think I need to conclude. Yeah, one more kind of point about this epsilon delta. So commonly kind of how people use the epsilon delta is that they specify this kind of a calibration point. So we pick a delta, pick a epsilon, and then that's our target. Now one there's this nice paper by George Kaisis and others on titled Beyond the Calibration Point, where they kind of illustrate that actually mechanisms, even if they kind of share this single calibration point, they might behave very differently. And if you kind of look at this in the FDP space, they are very different. So, and then kind of the attack bounds that they imply are very different. Okay. I think we pretty much went through this, but yeah, just kind of when you'll get the slides, you can check in more detail. So there's kind of like design choices, and also kind of when you're trying to understand DP applications, is kind of checklisting. Okay, what's the definition? What's the adjacency? It's not only kind of this add remove of substitute, but also question of whether it's kind of like user level, item level, whatever. Then these algorithms and budget. Kind of alluded, but wanted to kind of briefly mention this. So kind of, it's if we think about the nature of DP guarantees, so kind of if we kind of now think about the definition, it's a mathematical guarantee over all data sets, not just a particular one you happen to have. which also means that you can only prove it mathematically. You can never test it empirically. Well, I guess in some very restricted cases, I mean, you might be able to go through all pairs of neighboring data sets, but that's a very, very rare case. In theory, it's a so-called information theoretic guarantee, which means that it applies even against computationally unbounded adversaries. So no matter what kind of crazy quantum computer someone comes up with in the future, something protected with DP is in theory safe against these adversaries. So this is compared to typical security of cryptography, which is computational, and we assume that the adversary only has bounded computational capability. The caveat here is that this is, of course, assuming that you have a perfect source of randomness. Because if someone is able to break the random number generator you use, it's kind of, I mean, your DP guarantees are no longer very good. Some food for thought. Okay. Final slide. Kind of just quick takeaways. So I hope I managed to convince you that, I mean, DP is kind of a good tool for really allowing to build these provable privacy guarantees against attacks targeting a single privacy unit. We didn't talk so much about kind of the utility side of this. We will get more to that tomorrow. And but then, I mean, just saying that something is DP doesn't really say much. You need to think about, okay, what's the adjacency, what's the privacy level, and so it's kind of, there's a potential for some whitewashing saying that, yeah, our algorithm is DP, then in the small print, epsilon equals 1 million. And also kind of really encouraging you to, people working in DP to get familiar with the FDP, because it's a really nice way to characterize the privacy properties of the mechanism, and kind of these, which kind of the classical characterizations often don't really capture that well. Sorry for going a little over. Maybe we have time for some quick questions still if needed. But yeah, thanks all for your interest. Any final questions, or everyone eager to get to coffee? I'll also be here today and tomorrow, so happy to answer things offline. Okay, thanks.